Isso, exatamente. E aí, deixa eu tirar o som daqui. Exato. Então, cara, eu acho que assim, a fala dele, né, a apresentação devia ter umas 9, um pouco antes, né? Aí eu falei para ele que a gente não meia hora, mais ou menos meia hora. Boa noite, pessoal. Para quem não me conhece, eu sou Daniel, secretário do Comitê Técnico de Engenharia Aeroespacial da ABCM. Bem-vindos a mais um webinar promovido pelo Comitê. A palestra de hoje será dada por Tadej Semenic, que é um pesquisador que atua na indústria na Califórnia, nos Estados Unidos. Agora eu vou testar um pouco o meu inglês, tá? Good evening, everyone. Welcome to another webinar offered by the Technical Committee for Aerospace Engineering of ABCM. The dynamics of the talk will be as usual. After the presentation, the speaker will be available for a few questions. You can send your question in English or in Portuguese through the chat in YouTube, and we will read them to the speaker. Feel free to send the question during the presentation. However, they will be read only after the presentation. So today's talk will be given by Tadej Semenic. Tadej received a doctorate degree in mechanical engineering from the University of California at Los Angeles, UCLA, in 2007. He has more than 15 years of industrial experience, working mostly in the areas of energy transfer and storage and improving energy conversion efficiency. Tadej, thank you very much for giving this talk today, and you can start whenever you are ready.
Right. Well, thank you so much for this opportunity and for inviting me to present. Yes, so thank you to Leonardo, and thank you to you, Daniel and Emerson, for enabling these presentations. Let me go through outline of today's presentation. So I will first spend a few words just talking about my background, different areas that I've been working on. Then we'll go through motivation for this presentation, a little background about turbine engines, and then we'll look at the ways how to increase the efficiency for, in particular, for small turboshaft engines. And then we'll talk about the recuperators, and then trade studies analysis first, then design fabrication, and then we'll wrap up with the next steps on the first engine performance improvement, next steps, and concluding remarks, and what is the future work in this area. So let me begin a little bit of a background. So what I've done, the areas I've worked on. So I have similar background than most of the people I imagine are attending this seminar. As a mechanical engineer, I got my master's and PhD degree from UCLA. So that's where I met Professor Leonardo Alves. Is at the same department here. My bachelor degree is from Slovenia. So I'm originally from Maribor, Slovenia. It's at the border with Austria. In terms of work experiences, I started working as a thermal engineer at Amulet Thermal Technologies. I did quite a bit of work in designing and manufacturing thermal management products. Then I worked as research and development engineer, advanced cooling technologies. We did a lot of novel thermal management technologies development for transferring the heat, spreading the heat, single phase, two phase pump systems, and so on, heat exchangers. And since 2011, I have been with Teledyne Scientific. I started as research scientist, and then was promoted to senior research scientist and technical lead. I'm currently engineering manager. And the areas we work on is propulsion, heat exchangers, thermal management systems, energy storage systems, and high power, high brightness, light generating devices. So yeah, you could, your questions could be from today's seminar, or if you have any other questions, let's say from other areas, we're happy to talk about as well. So today's talk is going to focus on the first, where I put the blue box, on the propulsion and heat exchangers. So let me get started with a little bit of a background. So today we're going to talk about how to improve the energy efficiency, fuel efficiency for small unmanned aerial vehicles or UAVs. So they've been used quite a bit, different applications, situational awareness, precision targeting, logistical support from ground, ASC. And UAVs are classified in different groups based on the size, how much payload they can carry, how fast they can travel, and also the elevation, how high they can fly. So what we are going to focus here today is on the propulsion side, on the engines, and how to improve the efficiency. So that's the perspective that we're going to look at this. So the first group, the smallest UAVs are powered by batteries and electric motors. The next group, you transition to piston engines, and you can see, you can read the numbers and the example platforms here listed. Group 3, Venco or piston engines. And then when you get to a larger size, let's say over 1,000 pound vehicles, that's where transition to turboshaft engines. And then the largest group, the last one for very high altitude, 18,000 feet altitude, that's where it makes most sense to use a turboprop engines. So yeah, turbine engines, I'm quite sure you spent time studying them. They're very lightweight and compact in terms of how much power they can deliver, especially for high power 2,000 or more shaft horsepower. And they're very efficient. Just to give you a perspective, an example here, 10,000 shaft horsepower engine for a military transport aircraft, the A400M. It's a large aircraft, has an efficiency of 40%. So if you compare now to internal combustion engine, that's better than a diesel engine. So for example, gasoline engine is somewhere 30%, 25 to 30. And diesel is higher, especially large diesels, but this jet engine is even better. So and the key question I have there in blue, so can we use turboprop or turboshaft engine for smaller UAVs? There'll be a lot of benefits if this can be done. So the answer is yes, you can do that. So you can scale down the compressor diameter and turbine and combustor and make everything smaller. However, the efficiency becomes much worse. So like we saw 40%, this 40% actually becomes now 10%. Wow, that's the problem, right? Because now you need 4 times more fuel. So, and that is really the reason why piston or Venco engines are used is really because of the so much worse efficiency when you scale the turbine engine to such a small size. So, but if we can make this work, right? If we can improve the efficiency of small turbine engines, that will be very beneficial because they have quite a bit of benefits over piston engines. They're much better in terms of ramping up to full power and down, lower vibration, lower noise, improved reliability, and so on. There are several benefits. There are obvious benefits over battery-powered systems as well. So if there is a way to increase the efficiency to about 30% ideally, or even higher, then we could start implementing turboshaft engines for UAV groups 1 and 3, from 1 to 3. Let's say practically group 3 most likely, and then you can go to even smaller group 2 in size. So now let's talk a little bit about the battery powering. So everything is being electrified. There has been a lot of talk about electrifying large size aircrafts. And I just want to give you an example here. We are also very active in the area of lithium-ion battery packs development, from cells to large battery packs. So if you look at the specific energy, it's about 100 watt-hour per kilogram. So on the cell level, you will see record numbers, let's say 300. But when you start looking at commercial cells and building battery packs, there's some overhead there associated with this. So they end up about 100. So now if you compare to a recuperator turboshaft engine, this number will become 1,500. So it's a 15 times better specific energy or gravimetric energy density. In this particular example, I calculated was a 50 kilogram engine, which is actually at the very end. Last slide is the photo of that example engine. And if you use 50 kilogram of fuel, so that will be a particular example. So another interesting point that is, we're not thinking about it all the time, turbine engine or even a piston engine based UAVs, as you're consuming the fuel, your aircraft becomes lighter and lighter. So and actually that is what further improves your duration of your flight. Especially when you talk about larger aircraft, that becomes a very important aspect. But with the batteries, you have a constant weight, right? So the weight of the battery doesn't change throughout the flight. So there is really the bottom line important motivation why we are interested in improving efficiency of small turbine engines. So not to spend too much time, but just very briefly to overview background about turbine engines. So this is from Wikipedia, very simple image. So you have a compressor, will compress the air, and then compressed air is blown to the combustor. That's where you inject the fuel, and then the very important fact is that the hot air has lower density than the cold air. So then you have expansion that's happening. So your volume increases significantly when you are increasing the temperature of the air in the combustor. And then this high temperature, low density air then expands across the turbine, and it produces enough work that to drive the propeller as well as compressor. So that is very simple explanation how a turbine engine works. So now the higher the combustion temperature, the greater the efficiency, right? So now if there is a way to increase the temperature of the air getting into the combustor, what that means, you're going to consume less fuel. You will need much less fuel, and that is really the way to increase the efficiency, is to find a way to increase the inlet temperature of the air going into the combustor. So let me talk a little bit now the way how to increase the efficiency. Today we're going to focus on the regeneration or recuperation. So using the energy that is otherwise wasted. So what I have here is a cross-section to a recuperator turboshaft engine. So the simple explanation is the hot gas that's exiting the turbine is actually used to preheat the compressed air before it enters the combustion chamber. So for a small engine, this turbine exhaust temperature could be, it's about 700 degrees Celsius. And during normal operation, a small size engine, you will have a compressed air that's leaving the compressor about 200 degrees C But now what you could do with the recuperator is actually increase this air temperature to about 500 degrees Celsius. So let me explain this a little bit here. So I'm not sure if you see my mouse, but I'm pointing now in the front part here of the engine. So this is the first component, is the gearbox with the propeller. And then in the middle, we have a combustor, and over here, I'm pointing to, which is saying compressor wheel, that's the compressor, and then the opposite side, close to the compressor, is the turbine, and then the recuperator is here. So let me follow the air. So the airflow, this blue arrow shows it enters into the compressor. So compressor now will compress this air, a typical compression ratio for small engine, somewhere about 3. We'll see some numbers later. So from room temperature, we'll heat up to about 200 degrees Celsius. And then follow this blue color here, so that the air actually then travels along the engine to the backward, and then it turns around. And then it's as it moves through this path, is actually it's heated. So it travels toward the combustion chamber, and it's heated from 200 degrees to 500 degrees, just to give you some perspective. Enters the combustion chamber, then the temperature further increases. We'll see it's about 850 degrees C or so. And then this hot air expands, used to then propel, to rotate, spin the turbine, and then this work is actually used to move the propeller. But because the small engines, they operate at a very high RPM, about 80, 90,000. But the propeller needs to operate about 3,000, so you do need the gearbox, so you can reduce the RPM. And then what happens to the hot gas? So instead of just exhausting the hot gas from the turbine, now it's actually moved through the recuperator before it exits. And later we'll look at some details how that works. So this gives you an idea how the recuperator works, and this is not new, actually. I did some research, and right after the World War II, 1945, Rolls-Royce, Pratt & Whitney, Allison, they have tried recuperators, but it was never implemented because of the weight penalty, and of course you have the additional complexity, and as well as high cost. So yes, it's a great idea, it improves the efficiency, but if it costs too much, then you consume less fuel, but it doesn't make economic sense. So that's why they haven't implemented recuperators. So let me just show you a little bit of the rationale here, why for a Brayton cycle, why adding the recuperator will improve the efficiency. So yeah, here you can look at the enthalpies. We have a temperature versus the entropy on the bottom. So and on the left side, we have a Brayton cycle. On the right is the recuperated Brayton cycle. So between the compressor and combustor, we're adding now the recuperator. And I want to point your attention to the heat added part. So that is in this case, the temperature difference T3 to T2. See, and if you look at, compare the size of these arrows, will give you a perspective, right? So you need, let's say, a lot of fuel for a basic or baseline Brayton cycle, and then you're also rejecting a lot of heat. So your thermal signature of the vehicle will be easy to detect the baseline or engine based on Brayton cycle, because you will be ejecting the very high temperature gas. But now, if you get the same TS diagram for recuperated engine, you can follow the two equations and derive yourself, and you see why the efficiency is higher. It's actually shown here with this blue area. But what I want to emphasize here is the amount of heat added actually for a recuperated cycle is now much smaller. And also in terms of how much heat you're ejecting to the ambient, you can also see much smaller size arrow over here. So then your thermal signature will be also smaller. So what we want to conclude here is that with the recuperator cycle, you will require less fuel, and also you have your thermal signature will be smaller with the recuperated system. So let me show you then the next steps. So after this, that's a very fundamental observation. Then the next step is to dive a little bit deeper on the design side. So we used a thermodynamic model, MPSS or X cycle we have also used. These are very good commercially available software packages that allow you to model the engine. You can model the engine performance at different conditions, different altitude, different RPM conditions, and with or without the recuperator. And this was with the collaboration with another team. I put the reference here. They have done this study, and what it shows that if you're adding the recuperator, they have predicted here the level of improvement you will see in the thermal efficiency of the engine. So for example, this first graph, the baseline engine had a 15% thermal efficiency. Now with the recuperator, this can be improved. And there are a couple of different curves here. And the blue one is quite interesting here. The blue is the recuperator with a higher pressure drop. You can see at the lower effectiveness, it's almost linearly increasing the thermal efficiency. But that at some point it's actually is going the other way. And the reason is because this additional pressure drop that is expected for a recuperator with high effectiveness, it actually provides a negative impact. If your recuperator has a lower pressure drop, like the red curve, then it will be much more favorable. So this points the importance of making sure the recuperator pressure drop is low enough. Here we are showing the improvement in specific fuel consumption. So the higher is the effectiveness, less fuel you consume, and just give some actual numbers what to expect. Baseline is 1.6, and you can see the improvement that can be achieved. There is a slight penalty in the thrust. Baseline is 80 pound force. But with the recuperator, actually, you're losing on the thrust and the power. So what was not considered here was the weight, and that later in presentation we're going to emphasize that it's not only enough to look at the pressure drop and the effect on the engine performance, but weight is extremely important factor as well. But this is just to give you some idea. So, oops, I went the way. Now, next step, we actually look at 4 different engines that one of our divisions at Teledyne, they have been they're working on these 4 engines. So we used MPSS model to compare performance of this 4 example engine. Now, if you recuperate them versus you don't, and it's quite favorable in terms of thermal efficiency. Design 1, for example, very small engine, 34 horsepower, about 17% efficiency. Now with the recuperator, we predicted almost 30%, and then a little bit larger engine. And this is pretty much the trend, actually. The larger the engine, the higher is the efficiency for the baseline. But we could see also very similar trend for the recuperated engine. Looking all this wide range of engines, we could see 10 to 14% increase in thermal efficiency if recuperating the engine. And I'll just give you an example, like how these type of calculations look like. This is from MPSS, or we used also X cycle to do this type of calculations. So this first component here is the compressor. This is ambient air conditions, 15 degrees C. That's a small elevation. Not very high elevation. So what exits the compressor close to 200 degrees C, 56 psia. So you have a 3.8 times higher pressure. So then this air enters the recuperator, gets heated to about 500 degrees C, and that's what enters the combustor. And then combustor heats up the air to 800 degrees C, and this then expands to the turbine, exits, and this 560 degrees, for example, would then be used to heat the compressed air, and what exits is around 200. So these numbers are in full agreement with that statement I made before, that from very simple thermodynamic calculations, we saw that you will have higher efficiency and lower exit temperature. And this kind of gives you a little bit of a feel for an actual engine, what type of numbers you will see. And also I want to point out the RPM, 90,000. This is very typical for small engines. As you're scaling down the diameter, your RPM has to increase. Large engines are usually operating about 30,000, so that's 3 times faster at these speeds. And the output is it's 28 horsepower. So now, so we talked about quite a bit of the background now, the reason why you would want to improve the efficiency, thermodynamically, what type of improvements you would expect. So now we're going to talk a little bit on the next step in the development. So the next step is now the design. So after not being fully convinced, yes, the recuperator, that's for different engine designs, we see improvement 10 to 14%. This is a great idea. Now, okay, let's ask now the key questions, right? So let's design it and build it. And number one, what we have learned, and you see some more proof toward the end, is the lightweight. So the approach in designing and building the recuperator, you really need to make sure it's lightweight, because when you're adding recuperator, you're increasing the weight. This could be the payload that you could be using for fuel, right? So that's an important aspect. The second one, number two, I talked to you about the short story from the history. Recuperators were around after Second World War, but they were not implemented. The one big one was cost. So if you have this great idea, but if recuperator is too expensive, then it's really, it's not gonna go very far. So the number two aspect in designing is cost, very important. The third one, we have seen some trade studies from our collaborators, the importance of pressure drop. There was an example where if pressure drop is too high, you actually, high effectiveness is worse. So maintaining low pressure drop, extremely important. And then the last one is having a high effectiveness. And when you're evaluating, you have two ways to measure effectiveness. You can measure on the hot side, or on the cold stream. So you usually have four temperature sensors, and you can measure on each side. Usually we measure this effectiveness on both sides, and then compare or calculate the average. So now, after we have a little bit better sense of what is important, what goes into developing a recuperator, so I'll talk a little bit about different options here. So on the top left, it's a cross section of an example engine showing the different components from a compressor and a combustion chamber, a turbine, and there is a recuperator around. So if we zoom in into the recuperator, so you could expect there will be some sort of channels there, right? So you have to exchange the heat between these two streams. So you have a stream coming from the compressor and another stream coming from the turbine. So you have to now effectively transfer the heat between these two streams. And what am I showing here on the right side? These are a couple of example recuperator configurations that are being considered for small turbine engine and different vendors. For example, Série, they have a channels like this is formed actually from a stamped metal plates. They are bonded together. Then there are some other designs. I believe this was the ceramic where one stream, the blue compressed air flows inside the red on the other side. Another ceramic design, a modular, and so on. So the message here is there are a lot of different designs that have been looked at. Most of them are like we're showing here on the bottom, where you have a compressed air flowing to one side, and it turns around, it flows backward, and then to the combustor. And similar to let's say shell and tube heat exchanger, the red stream will be the exhaust from the turbine engine, where you want to find a way that you can really increase the thermal contact between the two. So you use some kind of baffles so that you can direct the flow around to increase the contact area. Or another option is that you have some kind of guiding structure, very lightweight guiding structure and tubes, so the compressed air will flow inside the tubes, and then the high temperature gas will flow outside. So there are a lot of different options. So it's every vendor will say, well, my way is the best way. So I cannot show you the exact geometry to what we had, but yeah, ours was one of these options we come across that resulted in the lightest weight and the highest effectiveness, the lowest pressure drop, and it's really the key question is here I have on the bottom. So which of these arrangements will give you the lowest cost, lightest weight, highest effectiveness, and will be overall the best solution. Yeah, so due to proprietary nature, I cannot show you here the details of our recuperator design, but I will be happy to share the results. So we did so we developed a very, very lightweight design. So for the entire engine, it was about 11 kilograms added. So in that you're adding to, let's say, about 40 or so kilogram of the engine or so. So of course it will, there is a penalty clearly. That's why you're looking to minimize that penalty. A very low cost approach. What we found is less than $10,000 for the entire recuperator. So we built subscale prototypes, and then we gradually scaled up to larger, and so on, and tested at different conditions, representing conditions of a small turbine engine. We have done some thermocycling. So this simulates the starting, turning on, turning off the engine. We did many cycles just to make sure the structure we develop is can sustain, is robust enough. So I did some very rapid quenching tests. For example, if you have a hot engine and then suddenly you turn off at the very low temperature conditions, so we tried that. And these are two graphs that are very important in evaluating recuperators. The first one is the effectiveness as a function of mass flow rate. Here we are plotting mass flow rate per segment. So our design was a tubular but consistent of many segments. We developed a recuperator model. This shows the dashed line, the effectiveness of recuperator with, as we predicted, and then experimentally measured. So we got quite a good agreement. We were about up to 60% effectiveness. And this, in terms of the pressure drop for different engine types and operating conditions, the pressure drop, you could see here from a total pressure drop of 10% to 25%, and also got quite good agreement with the model. A lot of good lessons learned in terms of what did we do right, what we could further improve. There were some additional pressure drops we had at the flow manifolds, at the inlet, the outlet manifold. So there's some area we'll be working on improving. But yeah, overall, very, very happy. So we're able to fabricate a recuperator, scale it up to a large enough size, test it, measure the effectiveness. We predicted about 60%, and the pressure drop was in about 10 to 20%, what we were hoping on. So let me just explain briefly what this means, this percent, because if you're not working on turbine engine, you may wonder, well, I know atmosphere, I know pascals, I know PSI. So usually you scale up, you divide your pressure drop in pascals or PSI, divide by the pressure of that stream. So for example, if you have 90 psi and you have one psi delta p, so you will do 1 divided by 90, and then you will add all other pressure drops. Let's say you have to add up all the pressure drops and scale them to see what is your total pressure drop in the recuperator. So now we wanted to see, okay, for this particular recuperator we developed and tested, so what are we looking in terms of the engine improvement? So we did 60% effectiveness and 10 to 15% total pressure drop for this particular condition that we modeled before. So our recuperator was a little bit on the high side in terms of the pressure drop. It was not the super low. It was not that red curve that we looked before. So it's more on the blue. But the good news is, and you're going to see later, the 60% was a good point. We saw 8% no improvement in thermal efficiency for the engine. What this will do is reduce specific fuel consumption for 40%. So that was quite encouraging to see. So what this will do will then result in increasing the range of a vehicle. There is a little bit of a penalty here because of this additional pressure drop. If you just take the 10% one, instead of 80 pounds force thrust, now we are about a little bit over 70. So 8%, what was it? But yeah, 10%, about 72. So 10% reduction in thrust. So let me yeah, so now let's go to the next step. So now, all right, so we have looked a little bit of trade studies first. We have went over what's important in design. We designed a recuperator. We built several prototypes. We tested. Then we compared performance plugged into our NPSS simulation, see, okay, what is the improvement you're going to see on the engine level. But now, okay, that's good. But what it really matters is the platform level, right? So what is this going to do to my mission, to the actual UAV? So we this model that we developed, we also included the weight of the recuperator, and have performed the studies compared to the baseline engine without the recuperator. And we look at an example mission for Shadow 200 RQ-7. So this graph on the bottom shows plots the flight time of a Shadow 200 as a function of total recuperator and fuel weight. So now, unrecuperated engine, the entire payload, everything can be used for fuel. So you have some. So the more fuel, the further you can fly, and you can see this is the blue curve here. With the recuperator, there's some initial penalty. You can see there's this offset. I showed about 20 pounds is our the weight of our recuperator. So, all right. So that is the weight you cannot have for fuel. But with our 60% effectiveness recuperator, this is this green curve, you could see we have much steeper slope because of this improved engine efficiency. You get to a crossover point. So that in crossover point is where you're not gaining anything. So if you're flying for a little over 1 hour, you're probably better off having unrecuperated engine. But now, if your mission is longer, which is typically you're talking 6 to 8 hours missions, now after 1 hour you start seeing a benefit. So you can see the green curve is now above the blue curve. So that means, yeah, you're benefiting a lot more by having the recuperator. So now, for an example mission, if you have 250 pounds, which you can use for fuel or recuperator, what we found here, well, the best is to use to have a recuperator 25 pounds, and then 225 pounds you use for the fuel. Now you can have a 6 hours flight time as opposed to only 4 hours. So you could see 50% increase in the flight time for recuperated for the Shadow 200 is using recuperated engine as opposed to the baseline engine. So, and then we also look at the recuperator with a really high effectiveness, 90%, because we have a good model and it's matching pretty good experimental data. So what we found that if we go to 90%, this will be much, much heavier. So, and that was a very important lesson here, because heat transfer background, you would always say, well, the higher effectiveness, the better. But in this case, that's not true, actually, because the weight penalty is just so high that after almost 4 hours, almost like at the end of the mission, you're barely reaching your crossover point with the unrecuperated engine. But yeah, in this case, we never reached the crossover point with 60% recuperator effectiveness. So this was an important finding here, that in fact, where we were going with low weight and about 60% effectiveness, that was overall much better point as compared to go to some very, very high effectiveness in terms of benefits to the overall mission. So now, yeah, let's talk a little bit about next steps here. So yeah, so we have a good concept here, good design. We demonstrated the recuperator by itself. So the next step is now really co-design together with the engine. Especially the manifolding, the outlets from the compressor to how you're entering the combustion chamber, making sure that you have a good flow, good mixing in the combustion chamber. All that has to be done together. Next step, we have built now a few segments. Now as we're building the engine, now we'll have to build the full-scale recuperator, integrate them with the engine. So once this is done, the very next step is the test stand, testing on a test stand. And I just found an example image. This is a turboshaft engine. It's a recuperated turboshaft engine on a test stand. You see all the components I show before the cross section. You have a gearbox, propeller, and here's the engine. Recuperator is outside. So the test stand, what it allows you to do, the engine is mounted, so you can measure thrust, you can measure the fuel consumption, temperatures and pressures and so on. So a lot of good measurements it allows you to do, and that's usually done in test cells. So after fully characterizing the recuperated engine, then you will start looking into installation on the actual UAV and then start doing the flight tests at that stage. So that's where we are. So right now we are ready now to go to the engine integration and then the tests of the engine with the recuperator. So let me just summarize the key take-home points here. So regeneration or recuperation can improve engine thermal efficiency from 10 to 15%. This number was actually obtained by simulating performance for different engines. There were 4 different designs that we evaluated. Very important lessons learned and important considerations. So if you're ever designing and building recuperators, so these are really important to keep in mind. Lightweight, there was a very good example there. We have seen 60% recuperator lightweight versus 90% recuperator that's heavier. So that's very important. Low cost, that's a must. You cannot be more expensive than the engine itself, so it has to be less than the engine. Low pressure drop. Remember, there were those blue and red curves that we have looked at, how important the low pressure drop is, and of course, high effectiveness. We built subscale recuperator all the way to the full-scale module, achieved low weight, low cost, 60% effectiveness, 10 to 15% pressure drop. And for what we predicted for the engine, it will reduce the specific fuel consumption for 40%, and this will then improve the efficiency of the mission. So instead of 4 hours, you'll be able to fly 6 hours. So you're looking at about 50% increase in the flight time for example UAV that we considered. And future work will work on co-designing recuperator with the engine, fabricate and test it on the test stand, and then further work on the integration with actual UAV and UAV testing. Okay, I think that's all. I would like to thank you for attending this seminar, and I'll be happy to take any questions, or if you want any more discussions on any of the topics, we can go back and discuss some more.
Hey, Tadej, thank you very much. It's a very interesting work. I mean, an important application. I think for the audience, it's. I mean, we have an audience with a lot of students, and we have also fundamental stuff. I mean, from thermodynamics and so on. And I think it's interesting for them to see what they see in the lectures applied for development of a new product. Very interesting. Thank you very much for the talk. I have a few questions. Okay, you can say. Sorry.
Yes, absolutely. Yes, please go ahead.
So we have a few questions, but first I want to make one question myself, because it's a little bit general. It's not actually related to the technology you've been discussing. It's actually, if you can say something about the path, the professional path from the academy, I mean from the university, from a doctorate to the industry. I mean, since we have a lot of students, graduate students, undergraduate students, I think it would be interesting for them to hear something about this path, if you can say something about it.
Oh, absolutely, happy to. Yeah, so yeah, and I can speak more about how it is in the US, and I believe a lot of this is talking to Leonardo as a similarity in Brazil as well. Yeah, so you have two paths, right, to decide after getting your PhD from aerospace or mechanical engineering. So you can go into industry, and we're going to talk about different options there. So that's one branch, which you're going to say, well, that's obvious. I know that, right? So industry, or you can go to academia. So what I want to talk is the sub branches now. If you go to the industry, you can go, more into product development, manufacturing. You can stay more in the research. For example, where I have been is it's between academia and product development. So we are doing a lot more research and development. So sometimes we stretch deep into fundamental science, where all this, what you're learning in school, and sometimes you need to learn even more. It applies very much every day. And then sometimes we stretch to the other side, to let's say some low volume production, and then at that point will be transferred to somewhere else, right? So the one thing I want to say is if you specialize in aerospace, doesn't mean that this is what you'll be doing until you retire, right? So what practically many times happens, especially if you work in the area of research, there are many adjacent fields that you have to learn about, right? So from let's say chemistry to electrical engineering, and these are all very beneficial, right? So like we talked today about the small engine right here. So this goes to mechanical engineering, chemical engineering, understanding how combustion works, the fuel conversion, structural mechanics, right? So the more open you are in learning these adjacent fields, the more it helps you in your career. And then you have typically two paths, right? So you can go a little bit more on the management path, or you can go into a technical path. These are both, there's none of them is like better than the other. Some people prefer go more on the technical path. What I have learned myself is you do not want to go to management path right away. So you do want to spend enough time in the laboratory, doing analysis, calculations, design, building things yourself, testing, because that really, really helps you later on. If you go to management path, because people come, they ask you questions, you need to be able to explain and answer. So that just I want to share with all of you. So, but yeah, in terms of academia, no, the other path. We work also with many professors. So you go on a tenure track. What is really important is your first 3 to 4 years. You want to make sure you establish yourself. You need to find your research topic. You need to publish enough and also good papers that you're recognized by your peers. And also it's good if you collaborate with the industry. That also helps you a lot. Yeah, so both paths I would say are good paths. So.
Okay, thank you very much. I have a question from Nelson. I'll try to translate. He actually asks about I think the term is payoff time. I mean, the time needed for the investment in a device, in a regenerator, the time needed to retrieve, I mean, the investment. I mean, I think you discussed the advantage in terms of time for mission time and so on. But maybe considering a typical mission time, how long would it take for the government to retrieve the money invested in such a device? Do you have a measure of it?
Oh, okay. Yeah, so the government-funded research is really looking to not necessary to get the payback right away. So that's one of the key difference in let's say the industry funding product development. You really look into near term. Usually you're looking for near term return. But the government investment is for much more long term. Just to give you a perspective, to develop a new engine, it takes about at least 5 years, and you need about 10 people. So that this picture we see here, right? So. Yes, and now you can convert, right? Whichever country you live in, Brazil or United States or Europe, right? So you need to have enough funding to be able to invest for this let's say 5 years. And the recuperator we talked today, it's a component, right, of the engine, right? So you will. And you will also have its own cycle, right? So you will also, let's say, take 5 years to develop. Now, if you can go together with the engine, let's say, team, you have enough funding. You have after 5 years, you have this new engine with the recuperator. You do need to have enough market, and we had struggle here with our company because we only focus on one sector of Department of Defense, and they just did not buy enough engines. So we had to actually, shrink quite a bit that department. It's important to also look at the commercial market as well. So if you can use your engine for commercial and military market, absolutely from day one, this is how you want to think about, right? And it's just like any investment banker, right? So you need to think about return on investment, right? So you need to see that you're gonna sell enough recuperators, enough engines that you get your money back, right? So, but yeah, these cycles are 5, sometimes actually 10 years when you're developing some new technology and implementing.
Okay. Thank you for the answer. This is a question from me again. Do you have you thought about the use of biofuel? I mean, I think maybe it's a tennis. At least people are investigating this in commercial flight and so on. Is it a possibility that you are already considering, or for the time, no, it's too early, the development to consider other fuel technology and so on?
This is very important topic actually. Yes, I would say especially for the ground applications, let's say for small generators, there are power generation, the ground biofuels. That's very important topic. there are some geopolitical issues before. I cannot remember, but there were some countries, they were just consuming too much of corn for producing biofuel, and it was just not enough for food, right? So these are just other things you have to consider with biofuel, right? Because you're then competing on the same market, right? That's used for food. But yes, if enough biofuel produced, absolutely, that's important aspect. And another one, you have to always think about the combustion reaction and how much carbon dioxide you generate, right? So if there's a way to minimize your carbon footprint, very, very important. So these are all things like for future, right? To think about how you can minimize.
Okay.
Yeah.
Another question. I'll translate it. Okay. Do you expect a decrease in the lifetime of the engine by installing a regenerator? I mean, do you expect a change in the lifetime of the engine?
Well, this is extremely good question. Yeah, there could be many answers to this question. It really depends on the approach. For example, I'm showing here different recuperator approaches, and some of them they were not that reliable. The recuperator itself was the weakest link in that case. So in that case, the recuperator could lower the lifetime of the engine, and that's what you do not want, right? So you want to ensure that the recuperator can overlive the engine. So I would say in the right way, you want to pick the design that is robust enough that you're that will be able to sustain the operating conditions of the engines. For example, I showed some graphs here. Very early on, you want to start doing reliability testing, like a thermal cycling, and to really make sure that your recuperator lasts at least as long as the engine. So the engines, they do have maintenance intervals, right? So so you could think about, if there's an idea, extremely low cost recuperator that you just, when you do engine maintenance, you just replace it, right? So you could think that way. But to summarize, the answer is you really don't want the recuperator to reduce your lifetime of the engine.
Okay, thank you. That leads to the next question. I mean, what's the relevance in the development of this regenerator? What's the relevance of material innovation? I mean, did you guys had to search for innovative materials, or did it play an important role in the development, in the design of your generator?
Very good question. Very good question. So we are thermal scientists and very closely work with. We have a material science group. So the two groups together actually came up with this idea. It was a big part was material development. So we developed some very, very lightweight ceramic materials that we have our own proprietary process, how we strengthen these materials and process so that we have some advantage there. So it was not just go out there and buy materials and assemble, but material development was important part of it. Characterization of those materials and making sure that they can sustain the conditions experienced in the small engine.
Okay, nice. Yeah, I thought, well, You have to have a lightweight device.
Oh, yep.
It's working in a very very hot environment and so on.
Yeah.
Maybe we may have to look at the materials you're using. So,
Absolutely. That was really the key, how it starts, that, right? So we had some novel materials here, and then we said, well, can we make heat exchangers out of this?
yeah,
Yes,
nice.
you can. And this led us to this recuperator application. Yeah.
Interesting. It was the starting point so for the idea. Nice. Another question is, can you say something about the complexity of the simulation model? I mean, what kind of physics? I mean, what kind of more complex physics that you maybe don't see in a undergraduate in the undergraduate course? Did the simulations consider?
Yeah, so let's look at some of this. Good, very good question. Let's see, I had some. Yeah, so you could do a lot of these simulations. Yeah, just the thermodynamics analysis, right? So knowing the entropies and the entropies. So there are two. Okay, let's see. The step one is the thermodynamic model that we talked about, X cycle or MPSS, which is allows you to calculate pressures and temperatures. So it in your cycle, this is the simplest model here, and you input parameters like compressor efficiency or turbine efficiency. So then is next level model is actually, all right, where is this 77% coming from, right? So this, you do need to run a specialized CFD model to simulate the compressible flow. So flow into your compressor, and this is usually you done this separately to model the compressor, and this is just the fluid dynamics a part of it. Then next level model on the compressor, you would do also the structural mechanics. So because now you have a high, you're compressing the flow, right, and then the blades are moving, so you have some stress on the blades, right? So these models quickly get quite complex. On the turbine, stress modeling, right, will be even more important, right? And now you have this rotating at a very high velocity. We saw like 90,000 RPMs, right? Yeah, this becomes, so in the practically you have several people actually here in a small engine. So one is usually one person specialized on the compressor and turbine, and then the king is usually the combustor. That's the most complicated. Then you have to actually model the flows, and many times you want to induce a vortex inside to improve the mixing of fuel and the compressed air. Then is the small modeling the droplets inside. So sometimes you have some type of slinger combustor where you have the shaft that spins is actually used to also supply the fuel, and as the shaft is spinning, is forming small droplets, and these droplets are ejected in the combustor. So you could actually go and model then. In some cases, you need to model the size of these droplets and how they are distributing. And then you could model then actually the combustion reaction as well, right? And it's a lot of it goes into designing the combustor, right? Like where is your air entering the combustor? Or maybe we can look at the other picture. Sorry, go back, or yeah, this one maybe. There are little dots here, right? So these are dots are here for the air to enter. It's actually, well, how many holes, the distribution, the diameter. So these are many CFD simulations you actually have to run on the combustor so that you get the right geometry. Because if you don't do a good job, you're going to get liquid fuel at the exit that will enter the turbine, uncombusted fuel. This will first, your combustion efficiency will be very bad, and then your turbine that's spinning in such a high velocity might not like it if you have large liquid droplets hitting the turbine blades, right? So so combustion modeling, that's usually, you have one person is expert on the turbine and compressor, but the combustor usually another person that expert on that level. And then is the next one that usually we forget, the bearings. Bearings extremely important, right? So you have something that spins 100,000 RPM, right? So you have a bearings, high stress, high speed, and also high temperatures. So sometimes you need to go to ceramic materials for bearings there, right? So a lot of work. So mechanical engineers and aerospace engineers, there's a lot of work in designing and building engine and the recuperator and other components.
Nice. And so the results, the simulation results that you showed today, consider all those physics, all those kind of simulations, all those kinds of simulations, computation.
This one, for example, this went a lot into this the designs, right? So I'm just showing some numbers, but to design this engine is that 5 years and 10 people.
Okay.
For each of this, because you have to really, if you start from scratch, right? You have to design all these components and flows, right, of the gases and fuel and
Okay, nice. I think that was the last question. Yeah. So with that, today, in name of the committee, in name of the technical committee, I would like to thank you very much to share such a rich experience with our aerospace community. Thank you very much, very much.
Oh, absolutely. It was my pleasure. Yeah. Thank you so much for attending this seminar. And I wish everybody Merry Christmas and Happy New Year and nice holidays.
Okay, I will speak just a few words em português. Primeiro, pessoal, assim, fiquem atentos, a gente vai continuar promovendo esses seminários, né? Então, fiquem atentos, a gente vai divulgar, né, nas próximas vezes, né? No próximo ano a gente deve fazer mais. A ABCM, em breve, ela vai atualizar as páginas dos comitês técnicos. Então, as páginas vão permitir que a gente traga um pouco mais de informação, né, sobre o comitê e as atividades do comitê, e vai permitir uma interação melhor também, né? Então, em breve, essas páginas vão estar sendo atualizadas. Eu queria também agradecer ao Emerson Batista, que é o técnico de informática aqui da Unesp de São João da Boa Vista, e futuro doutor em engenharia mecânica também. Muito obrigado. Ele que gerencia essas transmissões para a gente, então muito obrigado, Emerson. Queria agradecer também o pessoal da ABCM, né, que gerencia a parte de lá, né, da infraestrutura que a ABCM fornece para a gente, né, disponibiliza para a gente. Então, queria agradecer o Pedro, o Vinícius e a Débora. E com isso, desejo uma boa noite, boas festas para todos. E até o ano que vem, nos próximos seminários. Tchau, boa noite.